Hi, everyone. My name is Chien-Chin, and this is Iris. We are from Meta working on PyTorch distributed. Today, we are going to discuss distributed checkpoint. In this talk, the first part, we are going to discuss the background and the challenge of distributed checkpoint. And Iris is going to discuss the solution to the challenges. So first, why is it hard to do distributed checkpoint? It's actually not hard if we always save and load the tensor with the same parallelism and with the same word size. For example, in these figures, we have two GPU or like two ranks. If we start with DDP, and the DDP actually replicates the tensor, and we can simply save the replicate tensor in the distributed storage. Later, when we are going to load it back, we simply load this replicate tensor back to the model. There's no data shuffling required. What if we shard the tensor with FSDP? FSDP actually shard the tensor, but we still can save this sharded tensor in the distributed storage. Because we don't change the word size, we don't change the parallelism, we still use FSDP. So we can simply save this sharded tensor in the distributed storage. And then later, we load the sharded tensor back because the parallelism is FSDP and the word size is still 2. However, what if things change? What if the word size changes? Again, let's use FSDP as an example. We first use FSDP to shard the model, but we only have 2 GPUs, and then we save the sharded tensor in the distributed storage. But later, if we want to load the sharded tensor back, but now we have 4 GPUs, although we still use FSDP shard the tensor in a different way because the word size changed. Now we have 4 GPUs. So it's clear that some data shuffling is required in order to load the tensor back correctly. What if parallelism changes? Let's again begin with FSDP. Although we have the same word size, 2 GPUs, we first use FSDP to shard the tensor and store the sharded tensor in the distributed storage. But later we want to load the tensor back with a different parallelism, like a DDP. It's clear that we need to aggregate the sharded tensor, so some data shuffling is still required. This is the same if we want to load the tensor with different parallelism, even though word size is the same. We call this data shuffling resharding. In this talk, we define resharding as loading the saved tensor with a different parallelism or with a different word size. So some example use case like we can do training with some parallelism, and then later we want to do inference with a different parallelism. In this case, we need some resharding. Or another use case is we can first do offline training with a lot of data, and later we use the same model to do online training with less data. And in order to save a GPU resource, we might want to change the word size. In this case, the model and the optimize both are required to reshard. So the key issue for distributed checkpoint is that how are we going to save this tensor such that later we can load this tensor back with different parallelism and a different word size. So what are the challenges for resharding? There are actually 3 challenges if we are going to use PyTorch distributed native solution. The first challenge is the resharding flow. We need a checkpoint library to understand the resharding flow. Simply use torch.save and a torch.load. It's not going to work because torch.save and torch.load does not understand the resharding flow. An alternative solution is that we can save the parallelism and the word size information together with the tensor in the distributed storage. This works, but it does not scale. What if we have a new parallelism? What if we have a new combination of parallelism? We need to change the checkpoint library in order to understand this new parallelism or new combination of parallelism. So we believe a checkpoint library should be parallelism agnostic and word size agnostic, while still can support resharding. The next two challenges are related to static. Static is the PyTorch native solution to represent a model and an optimized state. The second challenge is the value of the static. There are many ways to represent a value being distributed. It can be shard, or it can be replicated. If we simply look into a tensor, we don't know whether it's replicate or it's shard. If it's parallelized by DDP, it's actually replicate. If it's parallelized by FSDP, this tensor is actually shard. So we need a definition. How are we going to save different type of value? For example, if it's tensor, whether it's replicate or shard. If it's D-tensor, how are we going to save it? The third challenge is the key of the static. The key here means like how are we going to identify a tensor? So for example, in a model, we might have a parameter called P1. And we can use this P1 to identify this tensor. And later we can save or load it back. Unfortunately, when we parallelize a model with different parallelism, the key are actually changed by the parallelism. For example, if we parallelize the model with DDP, the P1 becomes module.P1. If we parallelize the model with FSDP, P1 becomes FSDP underlying module.P1. So we believe like a future new parallelism should not change the keys. But we still need to support existing parallelism, like the most popular two, FSDP and DDP. So how are we going to solve these three challenges? Iris is going to discuss the solution.
Thanks, Chien-Chin, for explaining all the challenges. Let's talk about a solution that we have. So to solve challenge one, we're introducing a PyTorch native solution for checkpointing in distributed setting. So the Torch distributed checkpoint package is a parallelism agnostic, word size agnostic checkpoint solution. It supports saving and loading from multiple ranks in parallel. It also supports load time resharding, which enables like saving in one cluster topology and later load onto another. So for example, you can checkpoint during training with 8 GPUs, preempt the training, and later resume the training with 4 GPUs. Or you can train with GPUs and later load it back even without GPUs. So you may ask, how is DCP different from torch.save and torch.load? So first, DCP will produce like multiple files per checkpoint with at least one per rank. So say if you're training with 8 trainers, you will end up with 8 checkpoint files for each rank and additionally a metadata file. And another major difference is that DCP supports resharding. So in order to do that, DCP actually stores parallelism agnostic, word size agnostic tensors. That means DCP is not aware of any sharding information. It requires the sharding information to be provided prior to loading. What does it mean? It means that prior to loading, you need to get the model static or optimize the static, pass the static to DCP, and DCP then reshards the tensor based on the provided static sharding, and then use the pre-allocated memory from the static to load the data from storage. As you can see, DCP does not load the checkpoint into a separate Python dictionary. Instead of it just update the static you pass in place. So let's quickly look at an example of how to use it. So here on the left side, you see you can wrap a model with FSDP and set your static to FSDP's sharded static. Then you pass this static for DCP to load. And then on the right-hand side, you can see you can create a model without FSDP wrapping under a non-distributed environment. And then this is the main difference. You need to get the current static from the non-wrap model, pass it to DCP to load the checkpoint from storage. And then you can call model.load static to load all the parameters and buffer into the non-wrap models. But However, having DCP alone is not enough to solve all the three challenges for resharding that Chien-Chin just went through earlier. There is still the static value challenge as well as static key challenge, as DCP would require the static passant already have canonical keys and reshardable value. So let's first talk about like the static value challenge. Since DCP needs to support resharding, we need all the values to be reshardable. And to that end, we actually have our own resharding assumption, which I want to quickly go over. So we have D-tensor, distributed tensor with sharding placement. DCP would save each local tensor as a chunk in the respective checkpoint file. And for D-tensor with replicate placement, we only save one local tensor in one of the files for a given checkpoint. And for torch.tensor, we'll assume all the tensor with the same key are actually replicate across different rank, and we'll only save one copy. And here, because FSDP represents its local shard using torch.tensor, so internally, when you call model static, you need to convert the torch tensor to D-tensor in order to save all its local shard across different ranks. For all the other bytes, we'll also treat them as a replicates as well, and we'll only save one copy. So other than the static value challenge, there's still the key challenge. So DCP requires the key to be canonical. As you can imagine, that's what we're using, relying on to do resharding. So if a parallelism solution changed the static key name, DCP would not be aware of that, and it would result in a key error during loading. However, the static we get from directly calling model static or optimized static may not follow all the resharding requirements. And we realize it's actually not really easy for a user to solve all these three challenges during their checkpoint. So as it will require you to know a lot of implementation details of PyTorch as well as PyTorch distributed training solution. For example, you would need to know things like such as how each parallelism are producing their static. And you also need to know whether an optimizer is eagerly or lazily initialized. And for parallelism that does provide some sort of key and value conversion for you, user may need to call very parallelism-specific APIs. For example, in order to get the optimized static for FSDP that is reshardable, you need to call FSDP.optimizer static instead of the optimizer static today. So given all that, we want to introduce a more generic API that helps you to get a static that complies with all our resharding requirements and is easy to integrate it into your checkpoint flow. So we're introducing Torch distributed checkpoint static. What it does is that it will help you pre-process the static prior to saving and post-processing the static after loading. And it hides all the complexity from users. So when you're using our PyTorch distributed training solutions, it helps you get the static which the keys are canonical, the values are reshardable, and the states are allocated. So it will help you solve both the static key challenge as well as the static value challenge. So let's quickly see an example of how to use distributed checkpoint static together with DCP. And on the top, you can see that prior to calling DCP.save, instead of calling model static, you would, or optimize the static, you would use get static and get the model static and optimize the static that complies with our resharding requirements prior to saving it with DCP. So behind the scene, it actually does all the pre-processing for you. And on the bottom, you can see no matter whether you're doing a pre-training or fine-tuning, the flow are exactly the same. So in both scenarios, you will first get this call get static and pass the static to DCP to load from storage. And then after it, you call set static, which do all the post-processing behind the scene, as well as load it into the model for you to continue training or inference. So for example, we have like static options such as that. For example, on the right-hand side, for your fine-tuning use case, you can ignore all the frozen parameters, so you don't need to load tons of things that you're not using into your memory. So that's pretty much it, and just want to let you know that torch distributed checkpoint safe static and low static are available as beta feature in 2.1 stable build, and the gas static and sat static are actually experimental feature available in nightly. So we're actually really still debating on the API names, and we welcome suggestions from all of you as well. That's pretty much everything we want to cover, and we have a few minutes left if anyone has any question. Thank you.